The reconstruction of Marken Place Bridge and the span replacement at Benfleet Railway Station represent significant infrastructure upgrades aimed at enhancing transportation efficiency, safety, and longevity. These projects required precise engineering, coordinated planning, and the deployment of specialized cranes to execute heavy lifting and structural installation. The Marken Place Bridge, an essential link for vehicular and pedestrian traffic, was reconstructed to replace aging components, improve load-bearing capacity, and ensure compliance with modern safety standards. This complex undertaking required the careful dismantling of the existing structure, removal of deteriorated elements, and installation of reinforced steel and concrete components. A variety of cranes, including mobile and crawler cranes, were deployed to lift and position massive structural beams and bridge sections. These cranes provided the necessary lifting power to handle precast concrete segments and steel girders, ensuring precision placement to align seamlessly with the bridge supports. The use of advanced lifting techniques minimized disruptions to nearby roadways and ensured that the project progressed on schedule. Similarly, at Benfleet Railway Station, the span replacement involved the removal and installation of key structural elements that support the railway tracks and overhead infrastructure. Given the station's critical role in commuter transport, the project required meticulous execution to minimize service interruptions. The work was conducted primarily during planned railway closures, allowing cranes to operate efficiently in a controlled environment. The primary lifting equipment included high-capacity telescopic cranes and lattice boom crawler cranes, which were instrumental in hoisting prefabricated steel bridge sections into place. These components were pre-assembled off-site to streamline the installation process and reduce on-site construction time. The crane's precision control systems enabled the careful positioning of these heavy spans, ensuring that they met the necessary load-bearing and alignment requirements. One of the most challenging aspects of both projects was maneuvering large crane systems within constrained urban environments. At Marken Place, mobile cranes with extendable booms were strategically positioned to navigate through limited workspaces while maintaining optimal lifting angles. Similarly, at Benfleet Railway Station, the deployment of railway-mounted cranes provided enhanced accessibility to work zones situated directly above active rail lines. Engineers employed advanced lifting simulations and real-time monitoring systems to optimize crane operations, ensuring the safe and efficient handling of structural components. Weather conditions also posed a significant challenge, particularly during the lifting and positioning of large bridge spans. Wind speeds, temperature fluctuations, and potential ground instability were closely monitored to mitigate risks associated with high-altitude lifts. Crane operators worked in close coordination with ground teams and structural engineers to execute each lift safely, adhering to strict safety protocols and regulatory guidelines. The successful completion of these projects has resulted in significant benefits for both road and rail users. The newly reconstructed Marken Place Bridge now offers improved durability, enhanced traffic capacity, and increased safety for both vehicles and pedestrians. At Benfleet Railway Station, the replacement of aging spans has strengthened the railway infrastructure, ensuring long-term operational reliability and passenger safety. The strategic use of crane technology was instrumental in achieving these outcomes, demonstrating the vital role of heavy lifting machinery in modern bridge and railway infrastructure projects. Through meticulous planning, innovative engineering solutions, and the effective utilization of high-capacity cranes, the reconstruction of Marken Place Bridge and the span replacement at Benfleet Railway Station stand as exemplary cases of successful infrastructure renewal. These projects not only highlight advancements in bridge and railway construction techniques, but also reinforce the importance of precision lifting and structural installation in complex urban environments. Brighton Goods Bridge No. 6, also known as Rail Bridge 6, is a significant railway bridge located in the Battersea area of London. This is a complex 5-span bridge, originally constructed in 1913, featuring skewed crossings with varying angles across its spans. The bridge carries the Chatham railway lines from Victoria Station, crossing over several other railway routes in Battersea, including the Battersea Reversible Line, the Up Stewart's Lane Line, and 2 branch lines. Major reconstruction project. Around 2011, the bridge underwent a major reconstruction project to replace its aging Victorian-era structure. BAM Nuttall, the main contractor, appointed Kilnbridge as a specialist subcontractor to execute the complex temporary works and construction of a new concrete structure. The project required full reconstruction of the bridge while keeping the existing structure operational, ensuring minimal disruption to both passenger and freight railway services. The reconstruction of Brighton Goods Bridge No. 6 is part of a broader effort to upgrade railway infrastructure in the Battersea area, improving safety and operational efficiency for railway services. Delivering the reconstruction of Rail over Rail Bridge 6, Battersea, London. The reconstruction of Rail over Rail Bridge 6 in Battersea, London, was a critical infrastructure project aimed at modernizing and enhancing the structural integrity of a key railway crossing. This complex undertaking required precise engineering, strategic planning, and seamless coordination between multiple stakeholders to ensure the successful replacement of the existing structure without disrupting essential rail operations. The project involved extensive pre-construction assessments, innovative construction methodologies, and a well-coordinated execution plan that ensured efficiency and safety throughout the entire process. Project overview and objectives. Bridge 6, originally a steel-reinforced timber structure, had been in service for decades and was identified as requiring urgent replacement due to structural deterioration and increasing operational demands. The primary goal of the project was to replace the aging structure with a new, reinforced concrete bridge capable of supporting modern rail traffic while adhering to the highest standards of durability and safety. The challenge, however, was to complete this reconstruction without causing prolonged disruptions to railway services. To achieve this, the work was meticulously planned to occur in phases, culminating in a critical construction phase during a planned blockade over the Christmas period. Network Rail, in collaboration with BAM Nuttall, took the lead in the design and execution of the project, ensuring that all engineering, logistical, and safety aspects were carefully managed. The project's success depended on a combination of cutting-edge construction techniques, efficient material procurement, and rigorous quality control measures. Pre-construction planning and site preparation. A thorough pre-construction planning phase was essential to the success of the Bridge 6 reconstruction. Detailed structural assessments and feasibility studies were conducted to evaluate the existing bridge's condition and to determine the best approach for its replacement. Engineers developed comprehensive design solutions that would accommodate the operational constraints of the site while meeting all regulatory requirements. Stakeholder engagement was a crucial aspect of the planning phase. Regular consultations were held with railway operators, local authorities, and environmental agencies to ensure that the project met all necessary compliance standards. Additionally, risk assessments and contingency plans were established to address any unforeseen challenges that could arise during construction. To minimize disruptions to railway services, a phased construction approach was adopted. The initial phase involved the construction of the new bridge structure in the non-railway spans, allowing trains to continue operating on the existing tracks. This was followed by an intense period of around-the-clock work, strategically aligned with scheduled blockades to ensure efficiency and timely execution. Innovative engineering and construction techniques. The construction of the new Bridge 6 required the use of advanced engineering techniques to ensure durability, stability, and longevity. The primary material chosen for the new bridge was reinforced concrete, selected for its superior load-bearing capacity and resistance to environmental factors. One of the key engineering challenges was ensuring the safe removal of the old structure while maintaining the operational integrity of the surrounding railway lines. To achieve this, precision demolition techniques were employed, involving controlled dismantling procedures that minimized vibration and structural impact on adjacent rail infrastructure. The new bridge components were prefabricated off-site to expedite the installation process and reduce on-site construction time. This approach not only enhanced efficiency but also significantly improved safety by minimizing the need for complex on-site assembly. During the critical Christmas blockade period, construction teams worked around the clock to install the remaining bridge spans, lay new tracks, and reinforce the rail infrastructure. The use of specialized machinery, including tampers and ballast regulators, ensured that the new track alignments were accurately set to provide a smooth and stable railway surface. Safety and risk management. Given the complexities of the project and the high-risk nature of working in an active railway environment, safety was a top priority throughout the reconstruction process. A comprehensive safety management plan was implemented, covering all aspects of site operations, worker safety, and public protection. Regular safety briefings and training sessions were conducted to ensure that all personnel were well versed in best practices for railway construction. Strict access control measures were enforced to prevent unauthorized entry into hazardous work zones, and real-time monitoring systems were deployed to track construction progress and identify potential safety concerns. The use of innovative technology, such as remote monitoring sensors and automated surveying equipment, played a vital role in ensuring precision and mitigating risks associated with manual operations. Additionally, emergency response protocols were established to address any unforeseen incidents swiftly and effectively. Environmental considerations and sustainability initiatives. Sustainability was a key focus of the Bridge 6 reconstruction project, with several measures implemented to minimize environmental impact and promote eco-friendly construction practices. Efforts were made to reduce construction waste by repurposing materials from the demolished structure and incorporating recycled materials into the new bridge components. Dust and noise control measures were enforced to minimize disruption to nearby communities, and environmentally friendly construction techniques were prioritized to protect local ecosystems. Furthermore, the new bridge design incorporated features that enhanced long-term sustainability, including improved drainage systems, energy-efficient lighting, and corrosion-resistant materials that extended the bridge's lifespan and reduced future maintenance requirements. Successful project completion and outcomes. The successful completion of the Bridge 6 reconstruction marked a significant achievement in railway infrastructure development. Not only was the project delivered on time and within budget, but it also exceeded expectations in terms of efficiency and quality. One of the most notable accomplishments of the project was the early handover of the new bridge, with construction completed ahead of the planned schedule. This was made possible by the seamless coordination of all stakeholders, efficient execution strategies, and the dedication of the construction team. In addition to the structural enhancements, the project contributed to improved rail operations by providing a more robust and reliable crossing. The reinforced concrete bridge significantly enhanced load-bearing capacity, reduced maintenance needs, and ensured greater safety for railway traffic. The success of the Bridge 6 reconstruction serves as a model for future railway infrastructure projects, demonstrating the effectiveness of innovative engineering solutions, strategic planning, and collaborative project management. The project stands as a testament to the ability to deliver complex construction endeavors with minimal disruption, setting a benchmark for excellence in rail infrastructure development. Conclusion: the reconstruction of rail-over-rail Bridge 6 in Battersea, London, was a landmark project that showcased the best practices in modern railway construction. By combining meticulous planning, advanced engineering, and a strong focus on safety and sustainability, the project team successfully delivered a high-quality, future-proof bridge that will serve railway operations for decades to come. The collaborative efforts between Network Rail, BAM Nuttall, and other key stakeholders played a crucial role in the project's success. Their commitment to precision, innovation, and efficiency ensured that Bridge 6 was reconstructed with minimal impact on rail services while setting new standards in railway infrastructure development. Looking ahead, the lessons learned from this project will continue to inform best practices for future railway bridge reconstructions, reinforcing the importance of strategic execution, stakeholder coordination, and sustainable engineering solutions in delivering high-impact infrastructure projects. Precision engineering in action. The Reading Rail Bridge Reconstruction, Christmas 2011. The rail bridge reconstruction at Reading during Christmas 2011 was a landmark infrastructure project aimed at enhancing the resilience and operational efficiency of a vital railway crossing. Undertaken by Network Rail and executed by BAM Nuttall, the project sought to replace an aging steel-reinforced timber bridge with a robust modern structure capable of sustaining higher rail traffic loads while minimizing maintenance demands. Given Reading's strategic importance as a major rail hub, meticulous planning was essential to ensure a seamless transition from the old structure to the new bridge, all within a condensed construction window. The existing bridge, having supported the Reading railway network for several decades, exhibited significant wear due to prolonged exposure to heavy rail traffic and environmental stressors. Structural assessments revealed the necessity for urgent replacement, prompting Network Rail to schedule the reconstruction over the Christmas period of 2011. This period was strategically selected to coincide with reduced rail services, allowing an extended blockade for the complex operation. The project required a phased approach, beginning with preparatory works, site mobilization, and extensive prefabrication of structural components to optimize on-site efficiency. The new bridge design featured reinforced concrete, chosen for its superior load-bearing capacity, resistance to weathering, and long-term durability. Precast components, including deck sections and support structures, were manufactured off-site under controlled conditions to ensure precision and expedite the assembly process. One of the most technically demanding aspects of the project was the removal of the existing bridge and the precise installation of the new structure within the tight time constraints of the blockade. Advanced engineering solutions were employed, including high-capacity cranes and synchronized hydraulic jacking systems, to facilitate controlled lifting and placement. The dismantling process involved sequential cutting and removal of bridge sections to minimize impact on surrounding infrastructure. To mitigate disruptions and maintain track alignment integrity, state-of-the-art railway construction equipment was deployed. Track tampers and ballast regulators played a crucial role in ensuring the newly installed rail sections met stringent operational standards. The bridge replacement also incorporated modern rail fastenings and vibration-dampening technology to enhance track stability and passenger comfort. Executing a major infrastructure replacement within a compressed timeline introduced several logistical and technical challenges. Coordinating multidisciplinary teams, including civil engineers, structural specialists, rail operations managers, and safety personnel, was critical to maintaining workflow efficiency and adherence to project milestones. A 24-hour work schedule was implemented, requiring meticulous shift planning and continuous monitoring to address real-time engineering complexities. Safety remained a top priority throughout the project. Comprehensive risk assessments were conducted, and rigorous health and safety protocols were enforced to protect workers and ensure operational security. Environmental impact mitigation measures, such as dust suppression, noise reduction barriers, and controlled material disposal, were integrated into the construction plan to minimize disruption to the surrounding community. Despite the inherent complexities of executing a full bridge replacement in a high-density rail corridor, the project was successfully completed ahead of schedule. The new bridge was fully installed, tested, and commissioned within the allotted blockade period, allowing rail services to resume without extended delays. The early completion underscored the efficiency of the project team and the effectiveness of modern construction methodologies. The reconstruction of the Reading Rail Bridge in 2011 set a benchmark for future infrastructure upgrades within the UK railway network. The enhanced structural integrity of the new bridge has significantly improved reliability, reduced maintenance requirements, and bolstered overall network efficiency. By integrating precision engineering, strategic planning, and cutting-edge construction techniques, this project has contributed to the long-term sustainability and resilience of one of Britain's most critical transport corridors.